Hello everyone and welcome to our STEAM project number 15, featuring the Raspberry Pi Pico and MicroPython. This lesson is part of our Sherpa level series, designed for the somewhat experienced STEAM teacher. And today we are going to conduct some experiments and use the basic Python mathematical functions to calculate the speed of sound. My name is Peter, I am the founder of Educomondo and a certified STEM instructor and course designer. The goal of today is to develop a project to find out how fast sound travels by using an ultrasonic sensor. We are going to rehearse how to connect the ultrasonic sensor to the Raspberry Pi Pico, how to safely connect a 5-volt sensor output to a 3.3-volt input pin using a voltage divider, automate measurements through user-defined parameters, and most importantly, make sure your class works as a team to find solutions, help each other, and present their project in a clear way. In the Batman lesson, MicroPython lesson number 6, we connected the sensor's echo pin directly to one of the GPIOs. And although that did not create any issues, strictly speaking, we were running a risk by sending a 5-volt signal to a 3.3-volt pin. To put the dots on the I, we are now going to do it right and bring down the 5-volt signal to 3.3 volt. And we do that by building a voltage divider. We bring down the 5 volt to 3.3 volt by adding two resistors, one of 2000 ohm and one of 1000 ohm. Together this is 3000 ohm. Behind the first resistor of 2000 ohm, we make the connection to the input pin. Because the voltage at that point will be 3.3 volt, that's what we need. We get to that result by multiplying 5 volt with 2000 divided by 3000 or 2 divided by 3. This is a fairly straightforward project to build. We will need a breadboard with the Raspberry Pi Pico, the ultrasonic sensor, the HCSR04, a resistor of 1000 ohm and one of 2000 ohm, and a couple of jumper wires or preformed cables. You can always refer to the fritzing drawing so that your students won't make any mistakes. To start our program, let's go to our live Thonny environment. Welcome to our live Thonny session, and as you can see, I have already displayed the program on screen in our Thonny environment, which means that we will have another follow-along session. And we will start immediately by importing our libraries. We will use machine, we will use time, and we will also use UTime. UTime stands for microseconds, as you may remember. The next step is that we are going to set up our hardware, and we are using the ultrasonic sensor. So we have a trigger pin and we have an echo pin. The trigger pin has been attached to pin number 15, and because we are sending something from that pin, it is going to be a pin out. The echo pin will be a pin in. It's going to receive the signal, and we have attached that to pin number 14. In this program, we are only going to create one function, and that function is there to measure the distance using this ultrasonic module. So we will define measure underscore distance, and in the first instance we will set up the trigger. And the trigger is first set to 0. So we set the value to 0. We are introducing a very short delay of 2 microseconds. We set the value to 1 and we hold it for 10 microseconds. And then we set it back to 0. So that is going to give a burst of sound towards our object. Now, of course, we also need something to capture the return, the echo. And we do that in this while function. We will say while the echo underscore pin value is equal to 0, that is still our start time. If we see that it gets to 1, so if it changes to 1, that's the signal that it will be the end time. And the difference between the end time and the start time is actually the pulse duration. And we can use the utime.tix underscore diff and in between brackets end time, start time to write that in a very elegant way. The return of our function is the pulse duration. So far for our function that we will be using. What else do we need? Well, we need to ask the user for the number of measurements that they want to undertake. So, for instance, 10. The next thing what you need to get from the user is a known distance in centimeters. Why? Because that is going to be used to calculate the speed of sound. And then the last thing that we want to get from the user is the time span in between the measurements. So very simply asking, enter the time span in seconds between the measurements. And now we are ready to take multiple measurements and also in the end then calculate the average time. To capture all of the measurements and the number and the range that we have received from the user, we are going to create a dictionary. And we do that by the squared brackets. So the pulse duration is the outcome of the function, measure distance. And because we want to add each of these measurements, we are using append. So each pulse duration is going to be appended towards the dictionary. Now, don't forget that we are measuring in microseconds and we are using centimeters. But the final result that we want to see displayed is kilometers per hour. So we will have to do a number of steps to get from the previous one, so from the microseconds to go to seconds, and then from centimeters also to kilometers. And yes, you can do that in one go, but I know that quite a number of students may struggle with this, so let's take it step by step. So the first thing that we want to do is calculate the speed of sound in centimeters by seconds. And don't forget that because we use twice the distance, so we use twice the distance, it's 2 times the distance in centimeters divided by the pulse duration, and that pulse duration has to be divided by 1 million. Why is that? Because it's microseconds to seconds is 1 millionth difference, or 1 millionth of a second. The speed of sound in meters per second is once again dividing by 100, because centimeters to meters is a factor of 100. And then from kilometers per hour, it's once again between meters and kilometers, it's 1000, and seconds to hour is 3600, so it's 3.6, 3600 divided by 1000. So the kilometers per hour that we will display is once again the speed of sound in meters per second multiplied by 3.6. So you can see there's a number of calculations in between that your students definitely need to understand. In the next line, we are going to print the results for this measurement, and we are using in one line, so the F measurement, and in between the curly brackets, the measurement plus 1, so it's going to be measurement 1, measurement 2, measurement 3, measurement 4. Then it's going to say the speed of sound is, and then it's going to show the speed of sound in 2 decimals behind the comma in kilometers per hour. And then all of that will be displayed each time with the time span in between, the time span that we have received from the user. The next step is that we want to calculate the average speed of sound. So after we have done 10, 20 measurements, so the average pulse duration is equal to the sum of all the pulse durations divided by the number of measurements that we have conducted. And once again, we can do the same step-by-step calculation and conversion so that your students can exercise it once again, what they need to do to get from centimeters per second to kilometers per hour. So once that calculation is done, we have our final print, and our final print just is going to print the average speeds of sound is 2 decimals behind the comma x kilometers per hour. So I am curious, and here our setup that we have and that you can see at the bottom. So we have the sensor set at 0, and we have a box set to around 15 centimeters. So those are our variables, and let me run the program. So I'm going to have 10 measurements. The centimeters is 15, and I want 1 second in between so that it goes quickly. So our average here is 1236.97, so it's 1237 kilometers per hour, which is pretty close because the speed of sound is 1234 kilometers per hour. Now, there are some minor deviations depending on the humidity, on the temperature, and also some other ambient activities or ambient circumstances in the test environment. But I think this result is pretty close to what is seen as the average speed of sound, 1234. So I am very curious to see what your results are. I hope it works for you. So let's go back to our lesson. Here we are back in our lesson. So I hope this works for you too. And if not, well, you know it and your students know it. No time to panic, but to conduct some critical review of the code and checking both error messages and the physical project. Did you know that you can calculate the distance of a thunderstorm by counting the seconds between seeing the lightning and hearing the thunder? Well, the speed of light is a lot faster than the speed of sound. So when you start counting the seconds, the moment you see the light and you hear the thunder, then roughly you have to divide those seconds by 3, and then you will get a good indication how far you are from the storm. something that can save your life. And that's it for lesson number 15. I'm confident that you and your class found it very useful. In our next project, Project 16, we will take a look at one of the Sustainable Development Goals and explore how we can build creative solutions to tackle some of the challenges caused by climate change. I really look forward to seeing you again. Bye bye for now.